Okay, hello everyone. So this is part 2 of work and energy discussion. We're going to talk about the work done by a varying force, a changing force. So earlier we discussed work done by force, and we didn't specify what kind of force, but you saw that it's a constant force what we use. So for an example, let's say there's a horizontal flat surface and you have this box, some crate, that you want to move it from point A to point B. You apply a force F, and you move it a distance d. Displacement is d. As long as the object remains the same, as long as the mass or weight doesn't change, normally it doesn't, it stays constant. As long as the friction, the flow, these conditions don't change, the force remains the same. So the work is given by Fd, or better you can say Fd cosine theta, and then you know that this whole thing becomes 1, so comes back to Fd. So this is work done by a constant force. Even if you carry something up like this by applying some force, as long as the incline doesn't change, or the friction or any other conditions, the mass of the box doesn't change, the force doesn't change, right? So these are constant forces. Now if you plot this, a graph, we can plot displacement and force. I think we discussed this earlier also. Displacement changes, force doesn't change, so the force remains a straight line with whatever the newtons, like 10 newtons or whatever you are applying. So as long as it's a constant force, it's going to look like this. So this is what we discussed. So work is given by force times distance. And we can find plenty of examples where we use constant force. The other thing is, by looking at this equation, you can see we are multiplying this side work by this side, the distance. This is a rectangle, right? Area under the graph this colored area is a rectangle. So work, you multiply the two sides. In other words, you're calculating the area of the graph, and that gives you the work. Now let's think about a situation where force is changing. When you move something, the force you have to apply changes. Either it increases or decreases, or it goes up and down. Something like, think about a situation, you have an incline, but the slope changes constantly. Like you start here and then it increases, and then, right? So if you are moving a box up this weird looking ramp, you have to apply some force. Over here, you have to apply a bigger force because you are climbing a steeper hill. Over here, so the force gets bigger, right? Over here, force is even bigger. Here's an example. Force is increasing. So in this case, if you plot, this is just a hypothetical example to show you the situation. It won't be a straight line anymore like this. It won't be a horizontal line. Force is getting bigger and bigger. So it'll be something like, could be a straight line like this, the force is increasing. Or it could be something like this, we don't know. We have to try it out, do the experiment to figure out what it looks like. But what I'm trying to say is the force is changing. Another situation could be, you have a flat surface, you have the object. Let's say this is a container of water, right? And you are pulling it to the side, we are moving it horizontally, applying a force, but there's a little leak on the side, so the water is coming out. So as you move, the water level decreases, the weight decreases, so the amount of force you need to apply decreases. So here's a situation, it might look like this: displacement and force, it might go like this, decreases, right? So I'm showing you a bunch of examples where the force may not constant throughout the time, throughout the distance. Okay, so let's look at some math into varying forces. All right, so let me clear all this. A good example we can find in nature for varying forces. So going back to the same topic, work done by varying force. A good example, a common example we can see in nature comes from springs. Those little circular metallic things, looks like this, a spring. You can find these in your retractable pens and pencils, where you click the button, so the pencil, the writing part comes out, you click it again, it goes back in, like that. There's a little silver color spring inside. Springs are very common, many mechanical devices you can find these things. Such a simple piece of metal, but very unique. We can talk about a lot of physics properties of it. And why do we study these things? Why do we study this piece of metal? In nature, a lot of natural things exhibit spring-like properties. By studying springs, we can actually understand how a lot of things in nature work. For an example, force between molecules. Say you have two positive molecules. Could be two protons. It could be a positively charged ion and another positively charged ion. So when you try to move them closer to each other, let's say you try to bring this guy closer, there's a repulsion. This positive charges, equal charges they try to push each other away. This is like trying to compress a spring. You try to apply a force and make it compress, make it smaller. So the spring is going to push back, and the amount of force depends on how much you try to compress it, the amount of, like, the distance you try to compress it, right? Same thing here. The closer you get, more pushback, more repulsive force you experience, and using spring equations you can exactly calculate these forces. So if you study higher level chemistry or molecular biology, you will encounter these kind of situations, and spring equations are widely used to solve these problems. So we study springs because of that. Another thing is like compressions and stretching. I don't know the word for that. Compressions and the opposite of that in human tissues, human bones, they show spring-like properties. So a lot of things that stretch or compress acts like springs. So by studying springs, we can understand their behaviors. So we're going to spend some time talking about springs. So let's put this aside. Now let's say we have a spring. So we're gonna compress it or stretch it. If you don't apply any force, it has a natural length. Whatever that length, we call it the natural length. When you don't apply any forces. Now let's say you want to stretch the spring. You're going to increase the length of the spring. So we have to attach one side firmly to something. So here's the spring. This is the natural length of it. Okay, so let's say you measure this length on the x-axis. So you start here and then you apply a force. So because of the force you applied, so you're applying a force, now the spring stretches. Now it's here. So this is the length that increased. So you can apply a force and do this. Or you can do the opposite. You can apply a force on the spring the other direction and compress it like this. So now the spring is compressed. So originally it was here. Now it was compressed by a length of x. So this time you are applying a force this way. Now the important thing about springs, when you stretch, let's say we go with this first example. This is number 2. You're trying to stretch it, right? So here, going back, here's the spring. This is when there is no force. Now we apply some force, we stretch it a little bit. Okay, so we apply the force in this direction, we stretch it a little bit. If you want to stretch it more, you have to apply more force. Force gets bigger because the spring is pulling back with an equal force. If you have to apply 10 newtons to stretch it by 1 centimeters, the spring is pulling back with 10 newtons right now. Over here, if you have to apply 30 newtons to stretch it by 3 centimeters, right now spring is pulling back with the equal 30 newtons. The spring can do this until it breaks, until it loses the spring properties. So you apply a force, spring is pulling back. The more you stretch it, the more force you need, the more force the spring is going to pull back. So this force, we call it Fs, spring force. Sometimes we call it a restoring force, a force that try to go back, right? But normally we use Fs, spring force. The interesting thing is this Fs, or the force you have to apply, is proportional to the amount you stretch, right? You see that the more you pull this, so if you pull it even further, you need even bigger force. So if you plot this distance or displacement and force needed, or you can say let's say just force. If you don't stretch it at all, like right here, no stretching, no force, starts from 0, and then it increases as a straight line. Force is proportional to the displacement. This slope, it has a constant slope. Actually you can write a y equals mx type equation, a straight line. The equation becomes Fs equals k times distance, displacement. This is called the simple spring equation, or better we call it Hooke's law. Right? This k is called, or the slope of this equation is called the spring constant. A strong spring, a thick cable, a thick piece of metal, like a thick wire, and you make a spring out of it. If it is stronger, it will have a higher spring constant, means it will have a higher slope. That means even to stretch a little bit, you need a lot of force. You make a spring out of a soft, thin wire, it will have a lower spring constant. Means you don't need that much force to stretch it by so many centimeters or meters, right? These things should be in meters. So if you look at this equation, so I'm going to write it over here. F equals kx. This is in newtons, this is in meters, x is in meters, so therefore k units are newtons per meter. Also, for all our mathematical calculations, we can use it as F equals kx, but it's a standard when we write the equation, we put a little negative sign in the front. Why do we do that? What we need is actually the magnitude, the value of the when you calculate things, we don't have to worry about this negative sign, but this is a standard. The reason is we are talking about the force that's generated in the spring. You apply a force, like if you go back to this example here, you are applying a force to the right, but the force generated in the spring is in the opposite direction. It's always opposite to what you do. To indicate that, we put this negative sign in the front. Now it's the same situation if you try to compress a spring. So here's the spring, the natural length, and then you apply a force this way and you compress it. So here's the force you apply, here Fs, the spring is pushing back. So to indicate that the spring, the force in the spring is always against you, always against the direction you are increasing the length, right? In this example right here, you are increasing the length in positive x direction, but the force is increasing in the negative x direction. To indicate that, we put the negative sign. So again, in summary, here we have a varying force. Force increases or decreases, it changes with the distance. A good example is a spring, and how force changes with distance is given by Hooke's law, which is F equals kx. K is the spring constant, and the negative sign to indicate that the direction of the distance and force are against each other, they're in opposite directions, right? Okay, so let's move on. Let me erase this whole thing and start over. Alright, so let's think about a simple example. The equation we just discussed, F equals kx, Hooke's law. Let's say we have a spring, natural length 50 centimeters. Normally we don't need this in our calculations, and you stretch it (30 centimeters). You stretch it by 30 centimeters, and at 30 centimeters you have to apply a force of 750 newtons. To keep it stretched at 30 centimeters, you have to hold it with some force, so that force is 750 newtons. So the question is, what's the spring constant? So if you draw a diagram, so this is how it looks like, a simple sketch. So here's the spring unstretched. This length is 50 centimeters. Now you are stretching it. So you slowly increase the force until this length becomes 30 centimeters. At that point, the force needed is 750 newtons, right? You start from 0, you apply force little by little, 10 newtons, 20 newtons, 50, 60, 70, like that. You keep increasing. As you increase the force, the length increases, and to get it to 30 centimeters, 30 additional centimeters, you have to apply 750 newtons, right? At this point, you're applying 750. The spring is pulling back with the same amount of force. Now you can plug this into F equals kx. Force you have to apply 750. You don't have to worry about the negative sign. K times 30 centimeters, which is 0.3 meters. So K is 750 over 0.3 equals 2,500 newtons per meter. Alright, so that's how you find the spring constant. Okay, now if you plot this in the graph, displacement, usually we put D when it comes to work related stuff, but here let's say, okay, it's fine, let's say X and F. You have a graph like this. You can say at 30 centimeters the force needed is 750. This is in newtons. Let's say 0.3, so this is in meters, and the slope is 2,500. All right. Okay, so we talk about varying forces. An example, a good simple example is spring. Now let's see how work, the quantity work, get involved in varying forces. So I'm going to clear all this. Going back to the spring, now we know that work is defined as force times distance. There is a cosine theta next to it, but let's assume that we apply the force and the distance also in the same direction. So in this case, theta is 0, cosine theta is 1, so work becomes just FD, right? So for simplicity, let's say we apply force in the same direction. All right, so let's take this spring example. Here's the spring, and by applying a force, this is the displacement. By applying a force, you stretch it to a length x, applying F. We know that this F can be found using F equals kx, so keep that in mind, right? So if you plot the graph, this is the same graph I'm drawing for like the 10th time now. It looks like this, right? So F in newtons and displacement in meters. So in previous examples where force was constant, let's say pulling a box to a distance d, the graph we got was a line like this, force and distance, and we defined the work as the area, this area of the graph. So this is going to be same for the varying force as well. Even though the force is changing with the distance, the area of the graph, right, area under the curve, this area gives you the work. So for this example, for spring, work is again the area, which is the area of the triangle. So here we have a triangle. So how do you find the area of a triangle? We multiply the base, so half times base times height, right? So half times base is what? this amount that it stretched, x, height, force, half times x times force can be given as kx, if you know the spring constant, kx. So we have half kx squared, work done by a spring, by stretching the spring, work needed to stretch a spring by a length of x is half kx squared, and it's in joules or Newton meters. So keep that in mind. When it comes to work with a constant force, it's just Fd, or you can say Fx, force times distance. When it comes to springs, it is half kx squared. Okay, so we're gonna go take another step here for university physics. So if you are in college physics, you don't have to worry about this. Now let's go back to this. So for a spring, it's a triangle, it looks like a triangle, and we know that the equation is F equals kx. Now we want to find the work. So work is force times distance, or we can say force times x. X is also distance, same thing, we just use a different symbol. Now force is function of x, so we can write Fx times x. Now since the force is changing with distance, since it's not a constant, we can't simply multiply them. What we do is we have to integrate it from the starting point to the end point, 0 to x Fx dx. You know that we take a small area like this. Area of this is, if the force here is Fx, this width is dx, so that area is Fx dx, and to get the entire area, we're gonna integrate it from one end to the other end, right? So that way we can find the work for a varying force. So in this particular case, 0 to x, what is Fx? It's given by kx times dx. Now k is a constant, it's independent of the distance or anything, so we can take it out. So we have work equals k times 0 to x, x dx. And you guys know how to integrate this. This will be x dx becomes k times half times x squared 0 to x. Now if you apply this boundary condition, you get finally over here work equals half kx squared. Right? So for a spring, it simplifies to this. But you can get graphs like things are changing like this, it could be changing like this. So what you do is you plug the equation of the graph here to this Fx, and you do the integration from starting point to the end point. You can find the work. Alright, so we'll try some examples of these later in class. But for springs, very simply, if you remember this equation, half kx squared over here, half kx squared, that's all you need if it is just a simple spring. Okay. Alright, so real quick, let's try an example. So let me clear this one more time. So going back to the same previous example, we have a spring, we stretch it so natural spring, we stretch it by 30 centimeters and we have to apply 750 newtons for that. We calculated the spring constant to be 2500 newtons per meter. Question is how much work you do when stretching it from one end, from the starting point to all the way this 30 centimeters. How much work need to be done? Work equals half kx squared, half times 2500 times 0.3 squared, which is equals to, so use the calculator for that, gives you, looks like 112.5 joules. Okay, all right, let's do the opposite. Let's compress it. So initially the spring was here. Now we're gonna compress it by let's say 15 centimeters. How much work you do? This time you apply force this way, so work is again half kx squared, half times the same spring constant 0.15 squared, so 0.5 times 2500 times 0.15 squared gives you 28.12 joules. Okay, all right, so that's briefly work, energy. Now you have to spend this much energy, 28 joules of energy to do this work, energy, and how work and energy is involved in when situations where the force is changing. So we will work on few examples, a couple of examples in class, and I guess that's it. All right, thank you.